So what we will do is we will generalize many of the ideas that we have dealt so far, okay, in terms of dealing with many random variables and define what are called as random vectors. So far we have been dealing with random variables or two or more random variables. We will generalize this idea. So we looked at the joint density function, joint CDF of two random variables. For example, if x1 and x2 are two random variables, we defined joint CDF, PDF, PMF, and so on. For example, the joint CDF is denoted like this, which is defined to be probability that x1 is less than or equal to x1 and x2 less than or equal to x2 and so on. That is, both condition has to be obeyed. x1 and x2 may not be independent, in which case you cannot write this as a product of two conditions. Okay. So this is how the joint cumulative distribution functions are defined. Similarly, density functions, PMF, we have looked at all those things. Okay. And then for a discrete random variable, it is probability that x1 equal to x1, x2 equal to x2, and so on. Then we also looked at how to get the marginal density functions of only one variable from the joint density functions also. So now we can generalize it to n random variables. Initially we will keep them as a collection of n random variables. Then we will use the vector notation and make it more complex. So the idea just is a generalization. There is nothing conceptually new. You will be able to, whatever I write it down, you should be able to easily understand the reason behind it. So let us say we have got n random variables. We do not tell anything about their nature, their dependency and so on. Then we can define the joint CDF as the notation is fx1, x2 to xn of small x1, x2 to xn. The notation. And the definition is and it will have a usual property that fx1 to xn evaluated as minus infinity should be equal to 0 and fx1 to xn evaluated at plus infinity should be equal to 1. Then comes the joint. PMF is very easy. And so on. So if you then look at the joint probability density function, I am just writing the generalized notation. Okay. F x1 to xn of small x1 to small x. The convention holds good. That is, whenever we represent, we have a symbol in capital letters, it represents a random variable. There are n random variables. We are using this as a the subscript as a way to distinguish one from the other. The corresponding small case number is the realization of the random variable denoted by the capital case. How do we interpret the joint density function? So if we have f x1 to xn as the joint density function into dx1 to dxn is the probability that x1 lies between small x1 to this is the interpretation, and how CDF and PDF are related, same. Is given by this. So this is how the PDF of n random variables is related to the corresponding CD. Then what we can do is, suppose we want the marginal density function of one random variable xi given the joint density function, you integrate out whatever random variable that is not of interest. All things excepting I. So if you want, I can put minus into plus infinity dx I minus 1 and then dx I plus 1 all the way to dxn. So what we have done is we have left I alone. We have integrated out all other random variables over the entire, the x1, x2, xi minus 1, xi plus 1 all the way to xn. Then you will get this. You can also get the marginal density function of a subset of random variables. Okay, that is xi, xj, xk of xi, xj, xk if you want. So everything other than other than ijk, you integrate out everything else. And then if you now if you want to get the expectation, well, expectation means it has to be, you have to have one function on the, which is a function of all random variables. For which you can find the expectation. It is not like there is no corresponding way of expectation of a group of random variables. There has to be one function. So you can have a function g of x1 to xn. It may so happen that one or two random variables may not even appear in that functional form. Then it is only a function of the remaining one. But in general, we can always write it as a function g of x1 to xn, if it is that. Then if you have an expectation of this function, then the definition is how we have to get the expectation of a function of random. Suppose if g of x happens to be x1 then what you would end up having is E of x2. The reason is you are, see, only x1 appears here. For other things, you are just integrating it out. Okay, you are integrating out the other random variables. For x1 alone, you are multiplying x1 with, after integrating out the other things, you will have x1 remaining here. Fx of this one will be remaining, and effectively you will have only integration over this one. From this, it will be clear that all of them will get integrated out, and only the marginal density function of fx1 of x1 will remain. And because that cannot be just like that integrated out, because that there is a function. So that is what E of x1 will be. You can also put x1 x2 here. Then you will have E of x1 x2. Okay, but this is actually a function. Function which is a multiplication of two variables x1 and x2. That's all. So what we have done so far is that we have just generalized the concept of joint, density function, distribution function, everything for a number of randoms. Then before we get into, sorry, I wanted to keep this one for a reason, because I don't want to write it out against an example. Then I have to find these things like that. Okay, so we will come back and we will fill it up. I don't want to waste time on writing it out. We will make this before we get into the notion of random vector, we will just quickly recall. If we have a group of many random variables, there is something called as the covariance and correlation, which we just touched upon previously, to come into picture, because they may not be independent. We will just look at that. First, we have x and y are two random variables. We will look at how do we define variance of x plus y. So by definition, this is nothing but x plus y minus expectation of x plus y. The square of this. And then taking expectation. So if you use the notation E of x is equal to mu x, E of y equal to mu y, then x plus y minus mu x minus mu y. That you can write it as x minus mu x plus of y minus mu y square under x. Here, whatever you have variance, that number minus its expectation, square it and then take expectation. That is the variance. So it is x plus y. So x plus y minus of its expectation, which is minus mu x minus mu y. We can segregate it conveniently, square the whole thing and then take the expectation. Now if you do this one, this is expectation of a plus b whole square. So x minus mu x the whole square plus y minus mu y the whole square plus 2 times this is what you would get. And if you take the expectation, this is nothing but the variance. This is nothing but, on taking expectation, that is nothing but the variance of y. Plus we have a term which is an important one. That is called as the 2 times expectation of x minus mu x into y minus mu y. We will call this, define this as the covariance of x comma y. So we have this formula, variance of x plus y is variance x plus variance y plus twice the covariance of x plus x comma y. We know that the covariance of x comma y, if it is 0, then x and y are uncorrelated. We also know that if x and y are independent, they will be uncorrelated, but not necessarily otherwise. Then we will now explore this covariance of x comma y little bit. So this again we can multiply it out. You will have xy minus mu x y minus mu y x minus plus mu x mu y. So you will have e of x y. This is nothing but minus mu x mu y. This is a constant. You take this one, e of y is mu y. Again I can write it as mu x plus mu x mu y. So that is e of xy minus mu x. This is covariance of x comma y. So again this factor is we will encounter it very frequently, so it's better we give a name for it. That is called as the correlation of between x and y. So we have, this is R. And if two random variables have the property that e of xy is equal to 0, we say that the random variables are orthogonal. Again, just notation. Now we are all set to introduce the notion of vector random vectors. That is just for the compactness of representation. Unnecessarily having so many variables, everything. Then what we can do is we can define a vector of random variables. Okay. So if we have n random variables which we want to deal it together, they are all related. Okay, we want to deal in some scenario, we want to deal all of them together. Each one may represent different signals, but all these signals are used in our system. So we want to treat them together. Okay, and they may be related. And therefore it is convenient to come up with a vector notation in which all these random variables are found. So if there are n random variables, then we have a vector of n components. So how we can denote it as by means of a symbol like this. Again, we have to use a capital letter. We are already using a uppercase letter symbol for random variables. So for a vector, I will use this kind of notation. Okay. So it has the random variables are its form. The convention is you always, when we random vector, we mean the variables are arranged in the column. It's a column vector. You can also define it as a row vector and then deal with it, but this is the convention. So a random vector is nothing but a column vector of random variables which are involved. But although we can write it like this one, when we write it in a text, okay, it will occupy a lot of space. So what we will do is, we will say that you will use this notation. If you use a transpose of a random vector, that will have this form. It is easy to write because it fits in one line. So we will always, when we denote transpose of a random vector, it will become a row vector. So once we have denoted like this one, then we have to also, then the representation, all these representation becomes simple. If you want to represent f x1 to xn or x1 to xn, the joint CD, now I have to just use the vector notation and then write it as, that is what I mean by this is the random vector having x1 to xn has its component. Okay. So it's a joint CDF of a random vector, and within that the values that each random variable of this one takes, at that point I evaluate the CD x1 x2 x2. So that is again a vector of values. Okay. So that I will use again a symbol which is smaller in size as compared to this. I don't have any other way of doing it. If it is a book, we can use different fancy fonts. So I will just use this one, which simply means it is a vector of the values, which means that if I denote it like this one, it's just the values taken by the corresponding random variables. So if you use this one, then this is what we mean by the CDF of a random vector. The interpretation is that each of its variables, random variables, are less than or equal to the corresponding elements in this vector. So everything can again be now it will be the joint CDF, joint PMF. This would be the joint CDF, and so on. Then we can also define expectation of a random vector, which is element wise expectation of the representative random. But we have introduced the notion of random vectors and so on. But we will take up a simple random vector of a smaller size for the sake of illustrating certain concepts as an example, and how these variables can be related to each other. And in that case, how do we find the corresponding marginal density functions and so on? Let us take 4 random variables, x1, x2, x3, and x4. This is small enough to handle, large enough to illustrate the concept. So, how do we define x1 to x4 is that yes, it is some sort of a uniform distribution taking the values 4, but only in the range such that the condition that so if this is how the density function of x1 to x4 are being defined, you would see that some of them are dependent, some of them are independent. All these, it's not just four independent, just are standalone vectors which are being just put into a form for the notational sake. They have some relationship, and that makes for us to how to evaluate that each one of them. Help us to illustrate this concept. So now you want to find the marginal density function x, x1 and x4. Okay. So how do we find it? We have to integrate out whatever that is not of interest, x2 and x3. So x2 and x3 has to be integrated out in this. So we have one integral for x2, one integral for x3. Okay, and what we have to integrate out? This function. What is this function? It takes the value 4 only. But in a region, that is which is important. It is not just 4 you can put it and integrate. It is constrained by this condition. It is 0 outside. So this constraints will in effect only affect the limits of this integral. Other than that, we will have no rule. So that we have to put it properly. x2, if you look at it, x2 lies between x1 and 1. So we have to put it as x1 to 1. In this region only it is, then with some other condition on x2, x3, x4, then it will become this one. How about x3? It lies between 0 and x4. So if you then do it, so if you this 4 comes out, this is x3. So you just have, this is x4 only. That x4 is independent of this one, so you can take it out into dx2. And this is the x2. If you substitute 1 and x1 here, you will have x2 into 1 minus x2, n minus x2. So we can then write here x1, x4 of x1, x4 as, how is it? It is 4 times x2 into huh? Oh, x4. This is x. X4. X1. So it is, yeah, this is how you can do it. In a similar manner, you can find x2, x3. So I have to integrate out to x1, integrate out x4. x1, if I look at it, it is 0 to x2, and the x4 is x3 to x1, x3 to 1 into 4. So you will have 4, and this is nothing but I will have x4 into 1 minus x3 I will have, yeah? And then you will have x2 into 1 minus x3. Like that you will have. So you can find the joint marginal density functions of any subset. If you want to find fx2 of x2, you have to integrate out to the x3. Okay. So it's 1 minus half 1 by 2. 1 by 2 into this one, it is 2x. Like that you can find the x2 value, you can also find the expectation of x2. If you expectation of x2, one way of doing it is in this gen function itself you put x2 and then integrate out the usual manner. Integrate all variables with the g of x1 to x4 is equal to x2. If you do it, you will get an answer. But in essence, if you do that one, other than x2, all others will be integrated out, which we have done it in a two-step manner, and we have got this one, and then you will take the expectation. So that is nothing but 2x2, 2 into x2 whole square by 2. Okay. So what we have to do is integrate 0 to 1, x2 into 2x2 into dx2. This is what we have to do. So 2 into cube by 3, 1 if you have 2 by 3 or something you will get. Right? So you can find out individual expectations. Similarly, E of x1, E of x2, E of x3, everything can be found out. Then in a vector form, if you have mu x, which is all these can be written out in this using this. Okay. Then, when we had one random variable x, we defined variance. What is it? X minus mu x, the whole square, expectation. If you had two random variables, we defined covariance. Like this. Now, if you have a random vector, we want to define similar things. Okay. First thing is we will look at the correlation. How correlations are this one? They are the product of their first moments and then taking expectation. These are all central moments. Square of the central moments expectation. This is product of the central moments of x and y and then expectation and so on. The difference between correlation and covariance is This is all with regard to the central mode. These are all with regard to the ordinary mode, x, y, and so on. So here what we do is, for the illustration, we will take x, which is x1, x2, x3, and transpose is we will look at the vector. This is, we will look at the product of x with x transpose. That is going to be a matrix. So that will have, okay, this into this like that it will have. And so, okay. But let us say, so these are all actually, this is not compound. First of all, these are not compound. These are all random variables. Still we will retain that. If it is compound, it has to be small. So again, these are all what? Random variables only. Like that, you will have the matrix of random variables. Each one is a random variable or a function of random variable. X1, x2 is a function of random variable. Now, if you take an expectation of this, what happens? For that, first of all, we have to define what do we mean by expectation of a random matrix. This is a random, from random vector we have gone to random matrix. This is the straightforward definition is element wise expectation. So element wise, if you do an expectation, what is that you will get? Of this one. And so on. So what you will get is, these are all what are these, what is this one? This is the correlation between x1 and x2, x1 and x3. And so these are, you can call it as a correlation between x1 and x2, which is nothing but the second moment of x2. So we can use m notation if you want. M is what we are doing. M1 we are using for first moment, M2 for second moment, but you have in addition a notation to distinguish one random variable from another. So you can use a subscript. I can use that one, but I don't want to complicate it now. I will retain for this one x1 squared inside, x2 squared, which is then nothing but the second moment of the corresponding random variable. For this we have a notation, or x1, x2, or x1, x3, or x3, x1, and so on. Sorry, x2, x1, and so on. So these are all, this is a matrix where everything, the elements are all correlations. This is also a correlation only, special kind of correlation of a random variable with itself, which is what we are calling it as the second one. So this we will use the notation R x. So it is called as the correlation matrix. This will in a similar manner we can define covariance of a random vector. See, if it is a random variable, we do this one. Or if it is a random variable, covariance of a random variable with itself. What do we mean by that? Covariance, in place of x and y, you put x and x. It is expectation of x minus mu x into x minus mu x. This one is, which are what is the same? That is variance. So covariance of x with itself is nothing but the variance of x. Now we are talking about the covariance of a random vector. What it means is the covariance between different elements of the random vector. Each element is a random variable. So the covariances between different elements. x1 with x3, x4 with x7, whatever it is, you have to find all the covariances, all possible covariance between all the elements and arrange it in the form of a matrix. That is what we mean by a covariance of a random vector. So, okay, we can use some symbol C or something like that of x covariance. So, how should we define? Again, we will use the basic notation. Okay. If it is a correlation matrix, we define it as x transpose. But when it is a covariance, it is the central moments. Same thing we have to do with central moments. What do you mean by that? X has to be x vector has to be subtracted from its expectation vector. We can define E of x. So what we will do is, we will find what is this one? This is nothing but x1, x2 to xn. That is what is this one? Minus mu x1, mu x2 to mu x. It's just a corresponding this is what that would be. And that we have to multiply it by its transpose. First, and then take the expectation. This is just to get the arrangement of all the elements in this one, and then take the expectation of this. So here what will happen? You will have this structure. This is n cross 1, this is 1 cross 1. So you will have a n by n matrix. So if you multiply this and then take an expectation, you will get just the variance of x1. So you will get on all diagonals variance of x1, variance of x2, and variance of x3. And all these things are covariances, corresponding covariances. x1 minus mu x1 into x2 minus mu x2 expectation. That is the covariance between x1 and x2. and so on in a similar manner. So that is what we will call it as the covariance matrix. Now we can come up with another way of representing it. What is this? This one is, okay. We have looked at this one is nothing but e of x square minus e of x to whole square. That is what is variance. Similarly, you look at this kind of this. This is, I have derived it somewhere, I believe. Yeah. Finally, we have got e of xy minus ex dy. Okay, that is rxy minus mu x mu. You will have these are all rxy minus mu x mu. So I can write this. Each one is a one subtracted from another. The first component I can take it out and put it in one matrix. The second component I can take it out and put it in another matrix and write this matrix as one matrix minus another matrix. Component wise I will get multiplied. So this I will put it in one matrix. This I will put it in the corresponding element in the second matrix. This one, this one. If you arrange all these things, I get the correlation matrix. Okay? And this one will be a matrix. You will see that it is nothing but mu x mu y combinations. In fact, this is also same thing, mu x mu x. So what we will end up having is that we can write this like this. Covariance matrix is correlation matrix minus this kind of a product of the expectation, mu x matrix. So this will come here, this will come here. In a similar manner, we will get it. What is mu x that we have already of course, it's just an array of the corresponding mu x1, the whole like that. So this is how we can write it. So coming to give a practical example, if you have two of the variables ex1, you look at it. So you have to integrate out to 2. Okay. 2 lies between x1 to 1, 2 into dx. Is what I am saying. x1. What we are doing. Sorry, it's not expectation. We are only finding individual. This is what we are getting. So the marginal density functions we can get it like this. If you want to find E of x1, okay. Am I right? You just cross it. So into 2 I am getting. Into 2 is also there. So in this manner we can find out I think getting this one. Yeah, these are simple integrations. So in a similar manner you can find out the values will turn out to be like this one. E of x1 is 1 by 3. Is that what you are getting? 2 by 3. Okay, maybe here. So I have E of x1 is equal to 1 by 3. E of x2 is equal to 2 by 3. x1 square, x2 square, and we have got x1. These are the only big different things that we have. And their values will be 1 over 2, 1 by 2, and 1 by 2. So once we have this one, then the correlation, if you look at the R matrix, it will be E of x1 squared and E of x2 squared will be the diagonal elements, and this will, it's a symmetric matrix. So this will be on both sides. That is the correlation matrix minus mu x mu x. Mu x mu x transpose. That is 1 by 3 comma 2 by 3. 1 by 3 comma 2 by 3. That will give you this one. So if you subtract it, you will get C. So you can get the correlation matrix. You can also get the covariance. So this is how you will handle random. Then we will see later on Gaussian random vectors as a special case before we conclude our discussion on random.